Hello and welcome to this video on manifolds. Let's start with the temperature of the surface of the Earth, which is simply a map T to the real numbers R. We'd surely want this map to be smooth. But what could smoothness mean in this case? In fact, what could it mean for any map from some kind of object to another? In mathematics, maps and spaces are bound together tightly. For example, a linear map preserves the linear structure of a vector space, or a group homomorphism preserves the group structure. What could this mean in our case? Which kind of structure do the Earth or other objects need for smooth maps to be defined in between them? First of all, remember that differentiation involves taking limits, and every smooth map is certainly continuous. For these concepts to make sense, we need a notion of open sets in our space. This is provided for by calling our space topological. Furthermore, these limits ought to be unique. And so we require any 2 points of our space to be separated by 2 non-interfering open sets. This property is called Hausdorff. With this at hand, we can go back to the temperature of the Earth and find out which kind of structure smoothness requires. Now here comes the crucial observation. If we zoom in and look at the temperature locally, we find an ordinary map from some subset of R squared, which is given by the gray axis, onto the real numbers given by the red axis. But for this kind of map, we surely know what smoothness means. So how can we express the zoom procedure mathematically? Here is how. Our local set, let's call it U1, is homeomorphic to a subset V1 in R squared. That is, there exists a continuous map phi1 from U1 to V1 with a continuous inverse. This map is called a coordinate function. So what we actually considered when we zoomed in was the composite map T of the phi1 inverse, for which we surely know what smoothness means. Going back, we just zoomed in here, but we can also zoom in here, or anywhere, and find a map from R squared to R. In the end, we have covered the whole surface with sets and got an atlas of the Earth. Of course, there may be 2 or more charts covering the same area of the Earth. In this case, we require the transition maps, or coordinate transformations, phi beta after phi alpha inverse, to be smooth. Now we are ready to give the full definition. A topological space M is called a d-dimensional smooth manifold if it is Hausdorff, it is second-countable, it comes with a family U alpha phi alpha with open sets U alpha and homeomorphisms phi alpha, such that M is the union of all U alpha, and the transition maps are smooth. The pairs U alpha phi alpha are called charts, the whole family atlas, and the phi's coordinate functions. You might have noticed that we required our space to be second-countable. This makes every connected component of our space in a certain sense compact and ensures that integration will be well defined. So what about our map F between these 2-dimensional manifolds? We want it to be smooth, no matter which kind of local coordinates we choose. So we say it is smooth if psi beta after F after phi alpha inverse is smooth for all alpha and beta. If you'd like to dig a little bit deeper into this topic, take a look at the books by Spivak, Nakahara, or any other differential geometry or topology book. If you'd like to see more videos on certain topics here on YouTube, hit the like button, comment and share this video with your friends.